Hello, everyone. Welcome to today's webinar. I'm Gina Vitale, Assistant Editor at Chemical and Engineering News, and I will be moderating today's event. This webinar is titled UV-Vis-NIR Spectroscopy for Optoelectronic Devices and Materials, State of the Art, and is being sponsored by PerkinElmer. CNEN works with sponsors to identify topics of interest and value to CNEN's audience, and consistent with CNEN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of the screen or type your query into the Q&A box. If you are disconnected during the webcast, please log in again according to the instructions you received earlier. You are encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will be posing as many as time permits. Please note that CNN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at CNN online after the live webcast. The presentation today is being sponsored by PerkinElmer. PerkinElmer enables scientists, researchers, and clinicians to address their most critical challenges across science and healthcare. With the mission focused on innovating for a healthier world, they deliver unique solutions to serve the diagnostics, life sciences, food, and applied markets. They strategically partner with customers to enable earlier and more accurate insights supported by deep market knowledge and technical expertise. Their dedicated team of about 13,000 employees worldwide is passionate about helping customers work to create healthier families, improve the quality of life, and sustain the well-being and longevity of people globally. During the presentation, we will hear from Dr. Chris Lynch and Dr. John Bertels, both senior field application scientists at PerkinElmer. Dr. Lynch has more than 38 years of experience with PerkinElmer in a wide range of technologies, with experience in instrument control and data acquisition in various technologies. He has held positions in engineering and more than 25 years in global product management. He is currently supporting the UV-Vis-NIR fluorescence and thermal product range, consulting with customers on current and new applications, as well as working with the product sales team providing support and training. Dr. Bertels has almost 30 years of experience in broad areas of spectroscopy and analytical chemistry. He received his PhD from Tufts University in 2004, and since that time, he has used his diverse background to address challenges in inorganic synthesis and characterization, drug delivery, electrochemistry, and most notably optical spectroscopy. I will now hand it over to Dr. Lynch.
Thank you, Gina. UV-Vis spectroscopy is one of the most commonly used analytical techniques. Typically, they use sampling techniques that are cuvette-based, and they deal with liquids. In the development of engineered materials, UV-Vis-NIR infrared spectroscopy plays a critical role in a wide range of applications. These are ranging from glazing systems, optical materials, thin film coatings, paints, dyes, and the list goes on. In all cases, the spectrometer is important, but equally is the sampling accessory is critical in providing the most accurate results needed for today's applications. The most important measurement techniques needed for today's advanced material applications needs will be provided, and those techniques will grow as time moves on. A typical UV-Vis instrument covers a spectral range from 1100 nanometers typically to 190 nanometers. This will vary to some extent depending on the specific detectors used in the instrument. With the addition of additional components to support the near-infrared and the low UV region, it is possible to cover the range from 3300 nanometers down to 175 nanometers with a single instrument. This would be the UV-Vis near-infrared spectroscopy platforms. Solar emission is an important applications area for the UV-Vis near-infrared spectrometer systems that cover the spectral range from 2500 nanometers down to approximately 250 nanometers. In this spectral range, there are many applications covering what is called the solar spectrum. This is an important area for many instruments involved in a vast array of glazing systems from architectural glass to automotive and aviation, solar energy, and many other industries. All need the data provided by UV-Vis near-infrared systems to understand how their products perform and for manufacturing QC, QA, as well as research and development. The PerkinElmer Corporation was founded in 1937 by Richard Perkins and Charles Elmer. As the company grew, many new technologies and instruments were developed. In 1944, PerkinElmer launched the first commercially available IR instrument, the Model 12. In 1964, PerkinElmer acquired Coleman Instruments and continued to sell their UV spectrometer platforms, which were manufactured in Oak Brook, Illinois. From 1984 to 1996, a number of key instruments were released. The Lambda 9, 19, and 900 UV-Vis-NIR infrared spectrophotometer systems. With a significant number of enhancements, the Lambda 900 moved from being a spectrometer to a complete spectroscopy platform with an array of sampling accessories which provided a high level of flexibility. In 2004, along with the Lambda 900 spectrometer, the new unique accessory, the URA, Universal Reflectance Accessory, was released. This provided variable angle absolute reflectance capability, supporting the optics and laser industries and many others. In 2008, the Lambda 1050 was released. With enhancements to the platform, including access to a dual sample compartment configuration and new accessories to support the growing needs of the engineering material industries. Key to supporting these researchers and developers was the release of the TAMS, or Total Absolute Measurement System, with capability to provide angular-dependent measurements, which will be discussed later on. As the technology continued to grow and improve, some of the systems were now equipped with internal data stations to control the systems and provide readout. This is a big improvement over the old strip chart recorders. As time moved on, the development of desktop computers was also a welcome enhancement. The migration from an instrument to a spectroscopy platform has provided researchers, designers, and manufacturing companies with a platform that provides capability to expand as the needs change, where in the past years, the ability to increase the functionality of the system was limited by access to the sample area and the detector configuration. So where are we today? Well, UV-Vis-NIR infrared spectroscopy is considered a mature technology. Some drivers are changing that, though. Hardware improvements, software enhancements, better meeting user expectations. But really, the major change is the new applications that are requiring very specialized solutions, and also the industry adoption of specific new protocols and technologies. When discussing UV instruments, there are three general categories: entry, platform, and high performance, or HP. Entry-level systems typically are used in educational and industrial application areas, typically making measurements on a cuvette-based sample. The basic technology of the instrument may be a reverse optic design using a xenon flash lamp grating and a diode array detector. This combination allows the UV-Vis range to be acquired with a single flash of the light source. This configuration provides good performance at a low cost. Platform and high-performance systems typically utilize two sources, typically a deuterium lamp to cover the UV region and a tungsten halogen lamp covering the vis and near-infrared regions. Scanning monochromators are used to separate the energy from the source into monochromatic light, which is then focused on the sample. They also use dual beams, one sample and one reference, providing long-term stability. So what does platform versus high performance really mean? Well, the platform systems are the industry workhorses. The majority are double beam scanning monochromator instruments scanning the wavelength range from roughly 1100 down to 190 nanometers. Due to the double beam design, long-term stability of these systems is extremely good, which is important to industry. The high-performance systems are the most complex and provide the most capability. Utilizing double scanning monochromators providing very low stray light, they have the widest sampling configurations and also the widest dynamic range to deal with a multitude of sample configurations. We've discussed the high-performance measurement platform concept, and the concept is simple. Provide a high-performance double monochromator optical bench and the ability to interface a broad range of both standard and custom sampling accessories. This allows the needs of a new application to be met. As application needs change, the system configuration can grow as well. By simply providing easy access to both sample compartment and detector module, the measurement needs of a new application can be met with the same optical bench.
Two of the most common measurements we make with the UV-Vis-NIR infrared systems deal with diffuse transmission and reflectance measurements. So we're going to speak about those now. Spectrometer systems provide data in percent transmission, percent reflectance, and in absorbance, which is a calculated value. As the incident light interacts with the sample, there are a number of effects that can occur. The simplest of these is spectral transmission, where the incident light will pass through the sample with little effect. This is true for spectral reflectance as well, except in this case, the beam does not pass through the sample, it reflects off of the surface of the sample. Another mode called diffuse reflectance or diffuse transmission is caused by sample surface being rough or non-transparent. In this case, a focused incident beam will lose the specular component, and you will see a number of effects from this in the beam.
When light impinges on the surface of a material, it is either absorbed, reflected, or transmitted. The sample material, its surface finish, its clarity, is it clear or is it opaque, all have an impact. Does it have a mirror coating or is it a thick sample? All of these characteristics will have some effect. All of these examples will cause some level of diffuse transmission or reflectance impacting the characteristic of the sample beam. All need to be accounted for during a measurement.
In the simplest case, when a measurement is being set up, the first measurement is a baseline or background measurement, done with no sample in place. Next, the sample is positioned and the analysis is performed. In many cases, however, once the sample is added into the beam path, it will affect the position of the sample beam where it impacts on the face of the detector. In some cases, this shift in position can cause measurement errors or unwanted artifacts. This is simply due to the physical characteristics of the sample. Modern instruments have optics designed to compensate for this. However, it is not always possible. So how do you resolve this?
Integrating spheres are one of the most common of accessories used with UV-Vis-NIR infrared spectroscopy platforms. They are necessary for making a wide range of diffuse transmission and reflectance measurements, which could not be performed using a typical reflective detector configuration. The graphic shows the typical layout of an integrated sphere. Both reference and sample beams enter the sphere, which can range in size. The sphere is typically manufactured from a diffuse material. One of the most common ones is called Spectrolon. Shown in the blue spheres, as the sample beam from the instrument hits the wall of the sphere, it will diffusely reflect off of the wall of the sphere and will again contact the sphere wall and continue. Both sample and reference beams go through this process. Mounted to the sphere are the detectors, protected from first strike rays reaching the face of the detector by baffles. By the nature of the diffuse reflectance inside of the sphere, it will eliminate issues seen with a typical optical detector configuration. One thing to consider, the three images, B, C, and D, show the effect of a sphere material on the sample beam. In B, this is the effect seen when the sample is very diffuse in nature with little specular component. Image C shows the result when the sample has a larger spectral component. And in image D, this is the result of a very highly specular surface, such as a mirror. A very bright image, typically called a hotspot, can be seen. With highly reflective materials on integrating spheres, it is sometimes necessary to create a correction file to be used with these types of samples. All that is needed is a calibrated reference mirror, which is used to generate a new correction file. Integrating spheres are available in several sizes to meet specific application needs. Most spheres cover the spectral range from 2,500 nanometers down to 250 nanometers or lower. The detector configurations range from N-gas to PMT configurations or lead sulfide PMT detector configurations. And again, that depends on the application. The 150 millimeter sphere is the most flexible of the devices. It is commonly specified or recommended for use in many standards and methods. The design of the sphere is specified as to have specific size, port fraction ratio, and baffling around the detectors to protect them from first strike light. The 60 millimeter and 100 millimeter spheres are used in a broad range of applications where the specific configuration of the sphere is not defined. These are typically called relative devices as they would be calibrated to a specific analysis. Both the 60 and 100 millimeter configurations have specific advantages both in cost and performance. Typically, if the data is being compared across various labs or manufacturing sites, the 150 millimeter sphere is the best choice. One of the more unique accessories offered for the Lambda 1050 series UV-Vis-NIR infrared instrument is the General Purpose Optical Bench, or GPOB. This accessory is mounted in place of both the standard detector compartment and the detector module, and provides engineers with the ability to simply configure a test setup to make custom measurements. An array of optical breadboarding components are available, as well as many other suppliers' components can be used to build out custom configurations. Key to this accessory is the sphere detector that is used. The detector can be moved to any location and provides ports for both sample and reference beam. The sphere detector makes this kind of flexibility possible.
Flexibility is the key in sampling. Many applications require specific measurements to be made, and there are a range of configurations to satisfy the need. Percent TNR measurements on glazing materials is a common need. Accessories such as the ARTA accessory were designed to meet this need. Use of a high-precision stage and linear positioner allow the TNR measurements to be accomplished while maintaining a fixed position on the sample. The accessory also supports variable angle measurements. For this type of an accessory, a sphere is the recommended detector.
Absolute variable angle reflectance measurements are one of the most common measurements needed. The VW accessory, which mounts in the sample compartment of the Lambda 1050, was developed to satisfy that need. The VW technique eliminates the need for a standard mirror to be used to calibrate against. In many cases, it's a real challenge to find the standard reference mirror, and they are typically only calibrated at near normal angles. The VW name comes from the measurement configuration of the accessory. To measure the reference, the rotary stage is set to the V position. Once this is done, the sample is added, and a mirror is repositioned in front of the sample. In this case, the sample beam will make 2 bounces off of the sample surface. As only one surface has been added to the configuration, the sample, the %R is in the square root of the reflectance measurement acquired and is in an absolute format. The IV absolute reflectance accessory expanded on the original VW double bounce configuration, allowing smaller sample sizes to be analyzed. This is an important feature with the endless array of sample configurations and sizes currently being manufactured. The use of laser alignment included as part of the accessory allows quick setup and verification of the accessory's alignment. The unique optical path and double bounce configuration allow a much wider range of sample sizes to be analyzed. The UV-Vis-NIR Infrared Spectrophotometer has gone beyond being an instrument. Multiple detector configurations and a high degree of automation are needed to support the advanced application innovations of tomorrow. The need for an absolute reflectance measurements independent of an external standard has been a critical driver in the advancement of the analysis platform. As new product innovations are developed, the challenge to characterize these materials will grow. Ultimately, a flexible, automated platform is required to address the current and future challenges for optical measurements on a broad array of materials with ever-growing range of applications. So, let's look at some of those application areas now. And I would like to thank you, and I want to pass the baton over to Dr. John Bertels, my colleague. Thank you.
Thanks, Chris. So far, we have seen how and why high-performance optical spectroscopy has evolved in the way that it has over the years. Ultimately, it is the applications that drive the evolution. In all cases, the application challenges the instrument to generate data and information that is required by the end user. This leads to a varied and diverse array of application areas where materials characterization is required in some way. So, from the top, we have optical components such as AR, anti-reflective coatings, and high reflectance laser mirrors. Analysis of food and drink. Nanomaterials such as quantum dots and single-wall carbon nanotubes. Glassy materials for which there are a large array of application areas such as low-E glass to control energy costs and automotive glass. Paints and coatings also found in a diverse array of application areas as listed here. Color measurements is found in food packaging and consumer products, sometimes as a proxy for product degradation, or sometimes just for cosmetic appearances. And then finally, an equally diverse group of miscellaneous applications that are sometimes hard to characterize. The previous slide was designed to introduce you to the broad array of industries that utilize optical spectroscopy. So here we can focus on more specific applications. Optical components such as bandpass filters or dichroic filters are incredibly common but need to subscribe to very particular performance specifications to be effective. Aside from carbon-based nanomaterials, we could also include biomimetic materials or materials found in nature that we wish to understand in order to improve upon what Mother Nature has provided. Or we could consider the development of new cool roof coating materials as a means of controlling cooling costs in hot climates. These coatings must be checked and analyzed by a reflectance measurement using a high-performance instrument with an integrating sphere. Then finally, some additional applications to consider. Military applications are certainly a prominent area of interest. In the case shown here, camouflage went digital starting in the early 2000s because this appears to be more effective in field operations. This style is known as a pixelated style, and so there is a need to characterize these materials optically in a more precise way than was done before. This is an example where sample analysis areas can be relatively small, so care is required to do the analysis correctly. So let's now take a look at some of the accessories utilized by the high-performance systems for some of these applications. The URA, Universal Reflectance Accessory, was designed to measure the specular reflectance of materials, mostly flat samples, at any user-defined angle between approximately 8 and 60 degrees in an automated way, with no user assistance required once the measurement process had been started. Previous slides alluded to the complexity of recording absolute reflectance measurements in order to avoid the need for a standard of some kind, aka a relative measurement. So the URA was introduced to make the whole process easier and simpler for an end user. Part of that design requirement was the need to have samples placed horizontally, and in doing so, this reduces or even eliminates the human error factor introduced by placing a sample in a vertical position. As you can see, the URA is a modular accessory. Simply install, power up the instrument, and then you can begin. So what's going on inside the URA? How does it actually work? In this slide, you can observe the sample, highlighted in red at the top, placed horizontally. The URA contains a small slit on top. The sample, typically an inch in diameter, is placed over this slit such that a square beam of light, roughly 5 by 5 millimeters, is directed by the input mirror upwards to interact with the sample. The light then leaves the sample and hits the detector at an angle that is equal to the user-defined incident angle. Thus, a specular reflectance measurement is performed. The detector in this case is not a PMT, but a smaller, lighter silicon detector for the visible and a lead sulfide detector for the near-infrared. As you can see from the purple arrows, the detector assembly rotates in order to move to the defined angle of incidence. So this process requires two measurements, one with a sample of course, but before that can be done, another measurement must be performed without the sample of interest. This is usually referred to as a background measurement, or auto-zero, or correction measurement. The goal is to perform two equivalent measurements, one with and one without the sample, in such a way that we can then extract the true reflectance of the material. This previous background measurement is schematically shown here. If you compare this to the previous slide, you will see that the input mirror just below the sample has rotated down, and the detector assembly has moved in such a way that the total path length of the sample beam has not changed. In addition, the angle by which the detector assembly is held in place is the same as before. So this is an equivalent measurement, but with no sample introduced into the beam path. As such, we can now compare the two measurements as defined by those two slides. The difference between the two is simply the reflectance of the sample. Thus, we have designed a system that can perform automated, absolute specular reflectance measurements. Here's an example of some specular reflectance data for a laser mirror. A laser mirror is broadly defined as a mirror with a reflectance across some wavelength range of at least 99%, so it can certainly be higher than that. This particular laser mirror was measured at 5 different angles, from 300 to 1800 nanometers. In this case, both S and P polarized measurements were made, such that the average depolarized values were calculated and shown here. The shift to lower wavelengths as a function of incident angle is very typical for the interference type proteins typically used for laser mirrors. Note that one baseline is required for one particular angle, so 5 different angles of incidence would require 5 different baseline measurements prior to measuring the sample of interest at those angles. This does add to the startup time. Enhanced specular reflectors are mirror-like optical enhancement films that are integrated into the backlight of nearly all LCD displays, TVs, laptops, phones, and more. This reduces the amount of energy needed to power an LCD display and helps broaden the viewing angle by increasing the brightness of light coming through the display. These are shown in the lower right. Not only are ESR films designed to achieve very high reflectance in the visible spectral range, let's say about 98%, but they are required to achieve this high reflectance at any angle of incidence and under any state of light polarization. Therefore, the ESR films need to be measured with an absolute variable angle reflectance accessory, and the URA works very nicely. So we can see the flexible films here. They're very hard to mount in anything other than a horizontal position. And we see the subsequent data at 5 different angles. Once again, we observe a shift to higher energies as we increase the angle of incidence. Finally, we see here some reflectance data for the URA at around 193 nanometers. This is a very important wavelength for people in the semiconductor industry. Its fabrication of parts via photolithography on a substrate wafer is often performed at 193 nanometers. But it's critical that optical components are characterized at this wavelength. High reflectance values can also be difficult to measure at this wavelength, but the URA is able to perform this measurement effectively. To conclude, the URA is an effective and relatively low-cost automated option for reflectance measurements. There are, however, some drawbacks. Multiple baseline measurements for multiple angles and lots of moving parts to facilitate the automation process between background and sample measurements. It's for this reason that we now move on to the ARTA. The Automated Reflectance Transmittance Accessory, or analyzer, is generally considered to be the first goniometer-based accessory that was available commercially. It was developed around 2000 for the Lambda 900 and was then optimized and upgraded around 2007 for Lambda 950. As will become clear, the sample is inserted into the center of the accessory such that the sample and detector can move independently to generate specular as well as off-angle measurements. Indeed, essentially any sample detector configuration can be prepared in an automated fashion to generate reflectance as well as transmission data. The key features of this accessory were the incorporation of an integrating sphere type detector assembly, which is critical for these types of measurements. Furthermore, contained within the sphere were the powerful combination of a PMT and an in-gas detector for the near-infrared to offer unprecedented performance across the entire wavelength range. Lastly, a fiber optic bundle was used to feed the reference beam into the sphere, making this a true double beam integrating sphere detector. Here on the left, we see the ARTA sample compartment. The 60mm detector sphere labeled number 3 can be seen to rotate around the sample, placed at the center of the accessory compartment. Mirror 1 directs the sample beam towards the sample, in this case a piece of glass, such that the detector is collecting specular reflectance data. Note that the detector could be moved to any angle to collect off-angle data or even scatter data for BRDF or BTDF type measurements if needed. And this is seen here where the detector aperture has been modified to reduce the acceptance angle in order to improve the resolution of a scatter type measurement. On the far right, we see a tilt stage, which might be used for scatter measurements in those situations where the sample may not be truly isotropic, and a fuller characterization of the inherent scatter might be deemed necessary. The use of a goniometer type system is instructive since it serves as a reminder of some of the design limitations of commercial spectrophotometers. The sample beam, by virtue of the gratings and the optical path through the instrument, will not be completely homogeneous. This means that there is a need to collect two equivalent angles when trying to collect the most accurate data possible. In addition, there is another problem. Since the beam is not homogeneous, when we attempt to measure the sample relative to some background measurement, shown here on the left, the beam has been flipped, as it must, by virtue of performing the reflectance measurement itself. So this is simply unavoidable. The problem is compounded by the fact that the detector is also itself non-homogeneous, and different detector technologies will respond differently in this situation. The best approach is to employ an integrating sphere as a means of scrambling the reflected beam to remove detector bias, shown here. Data shown on the right illustrates the beam bias as seen for transmission data for infrasil glass at +60 and -60 degrees. The sets of data for equivalent angles are not the same, such that the two measurements must be made and an average calculated to generate a meaningful value. So here is some ARTA data. The ARTA was used to characterize various thin films which focus on solar type applications where the incident angle for the energy being exploited in some way may change over time, such as when the sun moves across the sky. In this case, a long-pass optical filter was evaluated. These materials selectively reflect and transmit designated parts of the solar spectrum for applications such as low emissivity window glass. It was anticipated that this type of film could be incorporated into a tandem photovoltaic, such that useful wavelengths of sunlight are collected, and the less useful wavelengths within the visible region could then be redirected to a second photovoltaic device with a more appropriate collection efficiency. As you can see from the reflectance and transmittance data collected at near normal incidence, the mirror film used here reflects visible light but transmits the vast majority of near-infrared radiation. A more exhaustive multi-angle measurement was then performed to see how these films would perform at any angle. The S&P polarized specular reflectance data show that the mirror retains its efficacy to block and transmit light effectively for all appropriate wavelengths of light for all angles. The ARTA has also been used to perform scatter measurements, in part to establish its potential in replacing more expensive single wavelength laser-based systems. Such is the case in this slide, where the ARTA was used to characterize the surface preparation of several randomly textured transparent conductive oxides, TCOs. These included doped zinc oxide and doped tin oxide. The data format shown here is angular intensity distribution versus scattering angle. Clearly, the data comparison between the two measurement configurations is very favorable. The ARTA is indeed an appropriate instrument for collecting scattered data. Finally, here is some representative reflectance ARTA data for an unidentified glass sample from 15 to 75 degrees. Once again, the equivalent configurations are shown here to illustrate how easy it is to set up the accessory to perform the appropriate measurements. To summarize, the ARTA has been the premier goniometer-based accessory for high-performance spectrophotometers for many years. It should be stated, however, that the cost of the ARTA, being an all-inclusive accessory with detectors and polarizers, was prohibitive for many labs, such that this accessory is often found in central research facilities and various national labs around the globe. Thus, in 2015, the TAMS was introduced by PerkinElmer in order to expand the popularity of this configuration and increase the size of the user base while lowering startup costs and providing additional flexibility for end users. The total absolute measurement accessory was introduced in 2015 to supplement the ARTA with a more cost-effective solution for a broader user base. Conceptually, the TAMS is similar to the ARTA, but with some key differences. The TAMS possesses a smaller footprint, exploiting the right-hand side detector area only and not the combined sample and detector areas as the ARTA does. The TAMS can measure larger samples, as seen on an upcoming slide, and the breadboard-based sample plate offers up additional flexibility for unconventional materials if needed. The control software is also the same for both the TAMS and the ARTA and is intuitive to use. As with the TAMS, only one baseline auto-zero is required before performing sample analysis for all angles. There is no need to perform multiple measurements beforehand. Most importantly, the TAMS detectors are modular. This gives the end user a choice in how to select data that is meaningful and sufficiently accurate for them and their analysis needs. The detectors are sandwich-based, consisting of, for example, silicon and InGas, or silicon only, and we will be discussing this modularity again shortly. So here is a cutaway view of the TAMS, complete with reference detectors. Unlike the ARTA, the TAMS consists of two separate detectors for the sample and reference beams. Thus, it is not a true double beam detector-based system. The sample stage shown here shows the default sample holder, typically for glass samples which range in size. However, this stage can also be used for smaller circular samples. Much larger samples can also be accommodated with some minor modifications. Here is an additional cutaway of the sample detector, showing in this case an integrating sphere-based detector. The lower image illustrates how the focusing mirror directs the beam into the sphere. This is critical for slightly curved or thicker samples. Finally, the two screws are highlighted here. These can be removed by the end user. This is part of the detector modularity I discussed earlier. So yes, the TAMS detectors are modular. This means you can utilize different detectors for different sample types or for different measurement needs. For example, a sphere-based detector will be fine for many measurements, but the need to obtain accurate scatter data, as an example, requires a more sensitive detector. Spheres are inherently more noisy, and they possess a more limited dynamic range, so these can be swapped out in order to perform sensitive scatter measurements if needed. Once you have removed the TAMs from the 1050, you can open the lid and simply loosen the 2 screws that hold the sample detector in place. This can be done in a minute or less. The reference detector would then also be removed. Both detectors would need to be swapped out appropriately, so this takes an additional 3 or 4 minutes. So we've opened up the discussion to include thoughts on the need for modular detectors. But why won't one detector do everything? As a reminder, here is the earlier schematic that shows how the baseline measurement and the subsequent sample measurement are always going to be different. The beam itself is not homogeneous. The detector used for both configurations is not sufficiently homogeneous either. So a true comparison between the 2 configurations, which then generates the data we are really interested in, is difficult at best. And there's another factor. What if we are dealing with a thicker sample, typically glass, for which the additional secondary, tertiary reflections are considered to be a critical part of the measurement process? In the image shown here, there are 4 sets of reflections that could contribute to the final observed reflectance spectra. Without a sphere-based detector, these photons would be missed and the data would be compromised. So this now leads to the design of multiple detector sets. Any or all of these detector sets can be used with the TAMs, and we can help you decide which ones are of primary interest for your needs. As an example, we split the detector types here into sphere-based and direct, where direct refers to a non-sphere type detector. These direct detectors are inherently more sensitive, but they usually won't possess the accuracy of sphere-based detectors due to the challenges highlighted earlier: imperfect samples, imperfect detector, imperfect sample beam, and thicker samples. Here's an example of the TAMS detector modularity. There are actually 3 options for the full-range silicon in-gas detector combination. This covers the range from 200 to 2500 nanometers. There are a number of additional options available for both the visible range only, as well as beyond the usual 2.5 microns. The standard combination is great for many routine measurements, for example, first surface mirrors or thinner glass samples. However, if scatter measurements are of interest, then a larger, more sensitive direct detector, which can also handle thicker samples without the need for an integrating sphere, might be more appropriate. The best option is then shown here. A larger detector with an integrating sphere with 2-stage thermoelectric cooling is the highest performing detector. Thicker samples and very low noise in the near infrared make this the premium detector option for the TAMs if needed. Reference detectors are shown here on the left as well. We will briefly touch upon some of the other sample compartment options. The modularity of the sample stage makes these options feasible. Moving from left to right, a silicon wafer sample holder, an auto-sample stage that allows the end user to manipulate the sample stage in order to either map a single sample or measure multiple samples, all automated. And on the far side, we have a simple large sample holder. More options are possible, of course. And now for some TAMS data. In this case, coated glass was measured in both transmission and reflectance mode at 30 degrees and 50 degrees, respectively. As expected, the AR coating shows low reflectance at about 400 nanometers. However, this depends upon which polarization state was used for the measurement. In this case, the emphasis is on angular accuracy and reproducibility. Many samples are designed to be particularly sensitive at higher angles. And again, this is also true for the polarization state of the light employed. In this case, the averages of positive and negative incident angles are presented. And the final data set seen here exhibits excellent reproducibility. Finally, in this case, we show a comparison of theoretical versus actual TAMS data provided by the Fresnel Institute in France. So we see here a combination of transmission and reflectance data for an unidentified sample. As you can see, the agreement between real and theoretical data is excellent. To summarize, The TAMS represents the latest manifestation in our ever-growing need to continually improve and upgrade our detector and accessory options for the high-performance instruments. But note that the TAMS and ARTA were not designed for all sample types, merely many of them. As described here at the bottom, textured and patterned glass is one area that really needs a dedicated accessory. These materials are designed to capture and distribute light, particularly in fenestration systems. So what is a fenestration system? Fenestration is essentially the science of building and window design, with a means to improve energy efficiency by pushing down heating, cooling, and lighting costs to lower values. There is a desire to control the distribution of light in a building as a means of controlling energy costs. In addition, light distribution needs to be designed in ways that are aesthetically pleasing and that enhance the experience of the building inhabitants. In many cases, a patterned textured sample is required, the nature of which is challenging to measure with most traditional integrating sphere options, such as the 150mm sphere. In this example, we see a sample that scatters light so completely that it is not possible to measure the true sample transmittance, unless the sample aperture is enlarged to capture all of the scattered light. The sample is designed to scatter light in this way, so the measurement process must be modified. The UL 270mm sphere actually contains two sphere ports for different types of glassy materials, and in many cases the large aperture is required due to this extensive scatter. Also note that a sphere this large is now required by the NFRC, National Fenestration Rating Council, for their procedure method for determining the solar optical properties of glazing materials and systems. So the UL upper-looking 270mm sphere is really required for any glazing or textured glass type application. The sample is placed horizontally, which is always the easier sample placement option. As previously mentioned, there are two port sizes, depending upon the level of scatter found within the sample. Both could or should be tried. Transmission and reflection can be measured at the same sample position without moving the sample. Larger samples can also be handled with an extended shroud or sample cover if needed. Here are some cutaways showing you how the 270mm sphere fits into the base instrument. As you can see, the sphere is large, and it has to be, so a larger sample detector compartment is needed to accommodate such an accessory. Indeed, even larger accessories have been designed for high-performance systems, but they are beyond the scope of this presentation. And here we see the anatomy of the 270mm sphere in a slightly different way. The sample is again placed horizontally for both transmission and reflectance modes. And beam switching between the two modes, reflectance and transmission, occurs via the internal polarizer drive, which shifts a mirror into position to redirect the beam upwards for a reflectance type measurement. So here is some data for the 270mm sphere. In this case, we are comparing the sphere with data from a much larger 630mm sphere based at the Fraunhofer Institute in Germany. We see excellent agreement between the 270mm sphere and the much larger 630mm sphere. In contrast, the 150mm integrating sphere in blue falls short in providing accurate data within the visible range. This would have major consequences for window and building design considerations. So to conclude, we've been through a whirlwind tour of some, but certainly not all of the major accessories that can be utilized for many of the optical measurement challenges of today. The open architecture of the Lambda high-performance systems, coupled with our various partner solutions, makes for a potent combination. You can build your lab from scratch, or simply add on as needed. We can help you with routine analytical needs, such as the 150mm integrating sphere, or we can help you define and design niche accessories, such as the 270mm sphere, and even beyond. Feel free to reach out to us with questions and comments. And so with that, I'd like to thank CNE News for hosting this webinar. And I'd also like to acknowledge Chris and various other colleagues at PerkinElmer for useful discussions that were had as the two of us went about building and compiling the content for this presentation. Finally, I'd like to thank each and every one of you for attending and taking time out from your day during this challenging time. We look forward to hearing questions and comments.
Thank you both for that presentation. We're going to move on now to some questions. We will start with this one. What is the difference in performance between a 60 millimeter integration sphere and a 150 millimeter or higher integration sphere?
Hi, Gina. This is Chris. I'll go ahead and grab this one. The major difference between the two is the larger the sphere is, the better integration you would get from the signal. So you get a more homogeneous signal and a more accurate signal. The other main feature with that is the fact that what they call the port fraction ratio, and that's the open area on the sphere relative to the total circumference of the sphere. For a 150 millimeter sphere is a much higher number. So the amount of surface area that you have to integrate the signal is much, much larger with a 150 millimeter sphere, and that's why they typically call it an absolute sphere. The 60 millimeter sphere, obviously, it still has the number of openings in it, both for the sample beam, reference beam, the detector and such that have been cut into the material, so you lose a lot of surface area with that, and that'll overall kind of impact the overall accuracy of the device. And that's typically why those smaller spheres are used for relative type measurements, where there's a standard that can be used to kind of reference the data against, sort of in a go, no-go kind of configuration, or a number of other tests where you're using it more like a collection device as opposed to an integrating sphere detection method. And that's really the big difference. The 60 millimeter sphere actually has a slightly higher signal output than the 150 does, simply because the sphere is smaller and you're getting the energy is more condensed inside that sphere versus with the 150 sphere. But overall, the 150 generally, if you're going to use it for measurements that are being made either to a standard or something traceable, or if you're going to be going between different labs and different manufacturing sites, the 150 is generally, I think, considered to be the most accurate device that you could use, as opposed to the smaller spheres.
Okay, thank you for that answer. And we're going to go on to another question. How the anti-reflection coatings of Rugate technology, apologies for my pronunciation, will be measured using UV-Vis spectroscopy?
Well, I'll take that one, Chris. This is John. So, yeah, AR coatings are, I think I mentioned in the presentation, are part and parcel of some of the technologies that we deal with. So the best way, there's two ways to do this. There's an absolute reflectance measurement process, and there's a relative measurement process. Personally, I prefer to try both. However, you might find that the absolute method with either the ARTA or the TAMS is the best option. Yes, you might need a more sensitive detector, as I highlighted in some of the slides, so the PMT and the ARTA might be preferable. The relative measurement process requires some kind of standard, and there are not that many materials that can be used for this kind of situation. So typically, a well-defined piece of glass, such as BK7 or fused silica, for which the values are well known, can be used as a kind of interim standard. Chris, anything to add to that?
No, I think you hit all the high points. Yeah, definitely the issue around the availability of standards to be able to use that kind of a measurement are difficult, but the points you mentioned, I think, are the best way to go.
Your standards that are traceable and are robust and do not drift over time.
Okay, great. The next question is, how can we calculate the oblique incidence studies for the thin film samples?
John, again, here I'll go with that. I'm not exactly sure what they mean by calculating. On the TAMS, on the goniometer accessories, you do have the additional flexibility to go to what we call high angle, or sometimes glancing angle. There is a limit, however. I think typically for the TAMS, it would be about 80 degrees. And in doing so, you would be able to interrogate more of the thin film, which is on top of the substrate. So those angles are challenging because alignment is critical, but that would be my best guess based upon the question.
All right. We'll move on then to another question. How many samples normally are needed to test the band gap using UV-Vis-NIR?
I'll go again on that one. It's okay, Chris. So I think, so very often band gap is done, or not always, but is often done on powders. So powder measurements actually were something we were going to put into these slides, but didn't have time for, as you can imagine. So there's a variety of protocols for that, and I can send additional information, but very briefly, the cup that's often used for these kinds of things comes in different forms, but it will be something around the size, say about a centimeter or maybe 2 centimeters, depending. But you'll need, many milligrams of material to pack that cup to a thickness such that the light, it does not transmit through the sample cup itself. You're essentially measuring diffuse reflectance. And then you can perform what's called a Kapelka-Munk analysis. But that is one way in which you can extract band gap measurements. Next question.
All right. So we've got another question that says, how can we measure the diffused samples like diffused glass or diffused lens?
Chris, do you want to add?
Yeah, I'll go ahead and take this one. Yeah. Typically, if you're looking at a diffuse sample, the only real way to measure it is, or the typical way would be with an integrating sphere, and you basically need to get the sample against the port of the sphere so that you're capturing as much of that diffused light as you can. And then typically you need to measure it both in transmission and reflectance to get the data from those, in those two modes, to be able to collect that data. And then from that, you'd be able to determine the reflection and transmission characteristics of the sample. But without a sphere, there's really so much light that is being deflected around the instrument simply due to the sample surface that you wouldn't be able to get a reasonable signal without the sphere. Do you have anything else to add to that, John?
Well, I would say, so the question of diffuse is, it's a broad question. So we mentioned scatter briefly. I mean, scatter is essentially a diffuse measurement in a different form, whereas in a diffuse integrating sphere measurement, you're collecting essentially all of the diffused light. In a scatter measurement, in a goniometer-based system, of course, you're slicing up that information degree by degree as you move around the material in space. You're slicing up the data essentially, and some people will kind of combine those two data sets. They'll do what's called a haze measurement at any particular wavelength, 500-600 nanometers, and they'll do a diffuse transmission measurement and a specular or total transmission measurement. And then they will compare that with the goniometer-based version. And in fact, they do get good agreement. There is a number of publications on this. So when someone says, do you want to measure diffuse, they might be, without thinking about it, they might be saying, I actually want to measure scatter. But it's a different part of the puzzle in how you characterize where the light is going when you interrogate a material, I would say.
Great, thank you for that. Could one of you comment on phase measurement via integrating sphere?
So in a sense, I just discussed, I mentioned, John again here, so I mentioned haze. It turns out this is a question that comes up because there are at least two different versions or definitions of haze. One is a very particular specific definition to a subset of many of these industries, and that's for plastics, and they have a method called the haze method, and that's ASTM D1003. And that is a very specific definition of haze and generates basically one single number for the entire visible wavelength range. And from that, they then characterize the materials. So for example, on the production line, across the week or during a manufacturing process change, they might look at these haze values in real time very quickly. Many people don't use that definition, though, without even being aware of that definition. They'll simply refer to, again, to go back to the previous comment about diffuse transmission versus total versus specular. What they're really saying is some combination of these questions. They want to understand where the light is going. So haze for those people is slightly different, and it's defined in a much more nebulous way by this kind of generic equation, diffuse scatter divided by total scatter. So it is not the best way to define the diffuse or the properties of a material, but it's just one way of assembling the jigsaw puzzle of what the material is actually doing when it interacts with the light.
Great. And I think we're just going to take one last question. Could one of you, Chris or John, talk about why the solar spectral range is so important?
Yeah, I can definitely take this one. The solar spectral range is really important because it really is probably covers the largest range of measurement types that we do. But they're also the things that are really affect most people sort of on a day in, day out basis. I mean, there's the energy conservation needs. Well, the solar spectrum falls right into that range where you're looking at the energy gains from heat gain, heat loss, for cooling, for commercial buildings and such, on being able to design effective energy control for those buildings. But then also it ranges into the automotive industry with the same thing with the automobiles. The amount of heat that's transmitted to the inside cabin of the automobile also means the amount of cooling that's going to be necessary to make the inside comfortable, and that impacts the design of the automobile, the fuel efficiency of the car because of the energy that's needed to drive the air conditioning to be able to maintain temperature of the car. Things like roofing for your homes, that range. Other things I don't necessarily think about with sunscreens for protection from UVA, UVB energy. Typically are done with big spheres, and typically the bigger instruments are used for those measurements. So it really affects really everything, kind of pretty much that you touch kind of on a daily basis. Fabrics for heating and cooling again. Fade resistancy of colors is another area that falls into that with the solar energy, how well the color's maintained, fabric aging, weathering of materials. Solar energy falls into that with the production of voltaic energy. So it's a very, very broad range of applications, and they're all based around, what is the solar spectrum and the distribution of that. So that's really I think the key is just the amount of application and need that directly impact kind of our daily lives as well as the health of the planet.
All right, thank you very much. And it looks like that's all the time we have for today. So thank you again, Chris and John, for your fascinating presentation. And thank you, participants, for being a great audience. Be sure to check CNEN or CNEN Online for information on the next edition of CNEN webinars. Thank you, On24 for technology and production services. And thank you, Perkin Elmer, for the sponsorship that made this interactive webcast possible. For CNEN webinars, I'm Gina Vitale. Goodbye.